Fun. This has been a great week hearing about all the different regimes of astrophysical turbulence. I've also been here since the beginning of the program. And we'll be lucky enough to stay to the end of the program, so I'm looking forward to continuing to be here. So, like Jim, I was inspired by Eve's reminiscences to go back and look, and thankfully I remembered this. It wasn't that long ago. 20 years ago at the Astrophysical Turbulence Workshop was actually the first time I came to KITP. I was a postdoc at the IS at the time. And as you know, KITP records everything, right? They're recording all of our conversation. You have to be very careful. However, it turns out if you go far enough back in time, something breaks. And thank goodness there were no copies of my slides, and there was no recording of the audio from that talk. So then I got a little bit curious, and I started looking at other talks, and unfortunately, the one that Peng has brought up a few times, where Andy Fabian and I had a gentlemanly disagreement, is nicely recorded and available online. There's a commonality you may have noticed between the people who have gone down memory lane in their talks. Any guess? Be careful. Princeton. It's not age. So I also did go back and look at the topics. So this is just a list of the first set of talks at the previous workshop. And I was also struck by something that Eve mentioned, that actually of the people here, only 3 of them have been at the program so far. That's Axel, Greg, and Ellen Zweibel, who was here earlier. And I think that's really a testament to the excitement and the younger generation of people that are really engaged in the field right now, which is a great thing. The other thing that was interesting is that this provided a way to sort of a perspective on what areas were really well represented in the conversations and discussions and talks we've had so far at the conference and the program, but actually weren't very well represented previously. So what fields have really emerged within turbulence that were not as represented 20 years ago. And the one that actually really struck me was the ability to now do plasma turbulence simulations, right? So there were, as Jim self-deprecatingly noticed, there were talks on numerical simulations and MHD of black hole accretion, but there really wasn't anything on trying to do turbulence simulations in kinetics and showing power spectra. And that really is something that's been enabled by the factor of million change in computation. And that kinetics, as we now saw, applies not just to the plasma kinetics regime, but also to the radiation kinetics regime, which Jim nicely described. So, okay, the organizers said I think they said 2 hours. I said, oh, I don't want 2 hours, I don't need 2 hours. So I'll just have a few observations about what we've talked about and then pose a few questions that maybe we can discuss for a little bit and then hopefully end early and go enjoy our Friday afternoon in Santa Barbara. So I think that one thing that has come out a lot in the different talks and discussions is that when we talk about turbulence in astrophysics, it's playing a variety of different roles, and it means different things to different people and is important for different reasons to different people. I think in many cases, what we're primarily worried about when we're talking about turbulence in astrophysical systems is really just the sort of outer scales of the turbulence that is dominating the redistribution of energy, momentum, chemical elements, that's setting the Reynolds stress, the Maxwell stress, that's moving around momentum and energy, et cetera. And the classic examples of this are, although we didn't hear a ton about that, would be stellar convection, right, or angular momentum transport and accretion disks, feedback and structure formation on all scales. And, I think honestly, to a typical astronomer who isn't that excited about turbulence in and of itself, right, this is the thing that's actually the most important and has the biggest effect on the evolution of astronomical objects, et cetera. But it is, in general, more problem dependent. There are less universal laws to be taken out, although there are some, right? Some instabilities like convection minimize the free energy source that's driving them. Other instabilities like the MRI in general can't do that because of external constraints. Gravity and cooling mean you can't wipe out the rotation entirely. So there are interesting general themes that emerge, but overall this set of applications is somewhat more problem specific. And then the more universal aspect of turbulence is the redistribution of energy in phase space. Typically, we think about that in the context of redistribution of energy in k-space, real space, but it also applies in velocity space as well, to scales where it is supplied by something on large scales like the first set of topics to where it's fundamentally dissipated and thermalized. And one thing that I was actually really impressed by just in all the talks is the extent to which this now is observable. This cascade is observable through a wide range of techniques in a wide range of different astronomical objects. So we heard about X-ray surface brightness fluctuations, velocity structure functions, right, both in clusters of galaxies, in the interstellar medium, density fluctuations in the interstellar medium. So we have a variety of different probes. If we're confident that what we're seeing in those observational probes is actually a turbulent cascade, that's extremely interesting because it provides a way to measure the heating rate of astronomical plasmas, which is otherwise extremely difficult to do. And one of the clear challenges that came up a lot in the discussions is, you know, if we measure some structure function or power law and density fluctuations from scintillation, you know, are we confident that we're actually measuring a turbulent cascade, and so we can use the normalization of those curves to infer heating rates. And that's a systematic uncertainty that, you know, we need to continue to struggle with. I think another general theme is that this redistribution of energy in phase space and how it's fundamentally dissipated on small scales, you know, this is particularly important, and this is part of the reason for the emergence of the importance of the plasma simulations in systems that are low collisionality, and so they retain memory sort of forever of how that energy was dissipated. It affects everything about the system, the temperatures, the radiation, the macroscopic dynamics, right? That's very different from stellar interiors, where we might worry about whether the Prandtl number, right, changes the properties of the turbulence, but we really don't care exactly how the atoms on small scales get heated, because that energy is thermalized so quickly by collisions. And then I think a third topic that's sufficiently challenging that it's sort of on its own is the dynamo problem, which came up a lot, right? Which is how does turbulence generated by many, many means, how does that rearrange the structure of magnetic fields, again, in essentially all of the astronomical objects we're worried about. And this has proved to be a very difficult problem, even in cases where we have tons of data, like in the case of the Earth and the Sun. We've struggled to have a good theoretical understanding, and that certainly, I think, still applies to astronomical objects. So at least for me, and I think everybody will be different on this set of questions, but at least for me, I was particularly struck and intrigued by subsets of the problems that we talked about where there's a real overlap between the astronomical importance of the problem and the need to really understand some aspect of turbulence to the extent that a turbulence theorist would agree that you're sort of struggling with turbulence, not just ram pressure or something like that on the outer scale. And we heard lots of great examples of that. Radiative mixing layers, multi-phase turbulence, which really sets the phase structure of gas in a wide variety of astronomical systems. So if you want to interpret emission line observations, absorption line observations, you have to understand this. It sets the cooling rate, so it affects the macroscopic evolution in that way. So these, I think, is a very nice example of a problem where the turbulence really does have a large macroscopic impact. Again, I already stressed this, the thermodynamics and radiation from basically all low collisionality plasmas. We heard about this, in beautiful detail where you can measure everything. And so we know many of the answers empirically in the case of the solar wind. We heard the nice example of pulsar wind nebulae and their radio spectra today. Neutron star magnetospheres didn't come up quite as much, but that's another application. Jets, accretion disks, etc. Another theme that came up quite a bit is, the extent to which one should think about turbulence as a random phase collection of fluctuations, as opposed to having more coherent structures and intermittency, and why for certain problems that's particularly important. So if you want to understand the role of cosmic rays in galaxy formation, we heard nice talks by Martin and Philip that the coherent structures of MHD turbulence might be very important for that. Scintillation as a probe of small scales in the ISM is in a very similar state. Another example is the role of understanding the initial mass function as a consequence of the density statistics of supersonic turbulence in molecular clouds. But it's not just a one-way street, right? These examples sort of emphasize how we need to understand turbulence, again, in a sort of turbulence theory sense to make progress on certain astronomical problems. But I think for somebody who sort of just likes turbulence because it's a great physics problem, right? One of the great things about astrophysics and about the examples we heard is that there are regimes of turbulence that Reynolds definitely would not have been able to do a laboratory experiment with back in the day, right? That was really restricted to incompressible fluids, which is still where our theoretical understanding and experimental measurements are the most sophisticated. But that is actually the exception rather than the norm in astronomical turbulence. We're highly compressible for different reasons. One, because we have supersonic motions on large scales. And then we heard about the really nice example today of radiation pressure dominated plasmas, where the fact that the primary pressure in the problem doesn't depend on density, it's just T to the fourth, means you can drive huge density fluctuations relatively easily. Another example in which there's been a lot of work that didn't manifest itself as much in the conference, but in which there's been a lot of work is actually the relativistic regime, where B squared is much bigger than rho C squared. We heard a little bit about this from Vladimir and Luca, and there's been a lot of work on this in the context of understanding neutron star magnetospheres and jets and potential connections to things like fast radio bursts. Okay. So I thought I'd end with a few topics that we can discuss for a few minutes before heading off into the sunset. I think it would be interesting to sort of take stock of what we learned over the course of the conference. And if you were, or if you are staying for the next month and a bit, what would you be interested in continuing to talk about? What are the topics that really struck you as particularly important? I think a particularly important question for the theorists to always keep in mind is, right, where are the observational and or experimental developments going to come that allow us to test our theories? We heard about some of these that I've listed here, and this is definitely just a sort of random late night collection, not comprehensive at all. Right, we heard about some of these we didn't hear as much about, but there's a lot of areas in which in all of these different regimes, we will have new and are getting now new interesting observational probes. And I think likewise, thinking about the change in the schedule 20 years ago to this year's meeting, what is it that people think will be new and particularly different in our discussions of turbulence on a 20-year time scale? I'll say something that I think definitely will be a little bit provocative. So my personal feeling is that plasma turbulence in particular is still in its infancy, and that in 20 years we'll find out that a lot of the results that we thought we believed and understood were artifacts of insufficient dynamic range in the problem between large scales and smaller scales, because we know this is an issue even in fluid and MHD turbulence, and it's an infinitely harder problem in plasmas where you have many different length scales you have to worry about. So, okay, so I'll leave that up there, and if people want to contribute to either of these topics or raise anything else for discussion, or vehemently agree or disagree with me, please feel free to do so.
You forgot to include gamma rays.
Yes, I did give the caveat that this is a non-comprehensive, and in particular, I was thinking here of sort of direct probes of turbulence. You know, I think gamma rays provide indirect probes. It's harder to get direct probes. I think there, the spatial and/or detailed spectral information really does help, right? So those were actually the examples I focused on had those features in common. There's lots of indirect constraints from electromagnetic observations more generally. In fact, there's even indirect constraints on this from gravitational waves. Two black holes collide, you set up these normal modes of the black hole, and there's evidence that those actually non-linearly couple, and that's been seen in the LIGO gravitational wave data. So even in gravitational waves, you have to worry about turbulence. All right, and I think we should be more than willing to end at an hour and 40 minutes before time.
I very much agree with your statement that in many cases, what is associated with the turbulent spectrum is not really a turbulent spectrum. It's a mixture of different contributions. And in particular, we know that in supersonic turbulence, we have a shallow spectrum of density fluctuations, and this is not turbulence. It does not reflect, for example, the dynamics of velocities. And therefore, it is very important to separate it. And a lot of work does not do this. We have just structure functions, for example. Sometimes they are proportional to densities, sometimes they are proportional to density squared. And therefore, for example, we were working on that. We developed the theory VCA, which velocity channel analysis, where we analyze this channel maps and then change the thickness of the channels, and we have predictions how the slope is changing. And using this, we can separate velocities and densities. And for centroids, we also developed the theory how to deal with this squared, for example, densities. And this is something which should be worked on.
Absolutely. It's clear that additional developments in that direction. And you know, I think the results we saw on the ICM and the CGM, I think, are actually particularly interesting. We precisely do not understand what is heating the ICM and the CGM. And we have these measurements that look like they're consistent with possibly being a cascade out of which one could measure the turbulent heating rate. And I think the question really is at the interface between the theory and the observation is to try to really understand the systematic uncertainty in doing that. So, any other CF?
I would say a lot of development on turbulence in the past 20 years happens in MHD region. So we understand it's very different from linear waves, but strong nonlinear interaction that give us MHD turbulence. It starts from analytical formulation and then has been tested by numerical simulations. Recently, with the power of numerical simulations becomes stronger and with higher resolution available, there's starting something new appearing that challenge the existing, like, accepted theory of MHD turbulence. So in addition to numerical simulations and observations, I would also want to see more development and more contributions to fundamental theoretical physical understanding of turbulence and MHD turbulence. And also about numerical testing, I also would like to see, like I think we discussed this on Tuesday, like different groups, and they tested the problem with the same setup, numerical setup conditions, and there's a fair comparison of different theoretical understandings. And observationally, there are many new observational techniques developed based on our physical understanding and theoretical testing. And also would like to see, well, we know that the best place to test the turbulence is our solar wind, because it's a local in situ observations. So I also want to see more like crosstalk between the solar wind, the plasma physics, and astrophysics, and toward a more comprehensive understanding of turbulence in diverse environments.
So could I just follow up? So you said recently something has emerged which fundamentally changes our, so what are you referring to?
I don't know if it's a fundamentally change or phenomenologically change. I'm talking about the plasmoid that where it happens everywhere, the tearing.
I see, yes.
Yeah.
So that's, for those who haven't followed, there were some very nice analytic predictions that as you go to smaller scales in MHD turbulence, you develop these sheet-like structures, and at some point they become unstable to the tearing instability, and if that instability grows fast enough, it changes the dynamics of the cascade. I think the question is, you know, in different astrophysical regimes, that can set in on different spatial scales. And so it'll be important in some regimes and not as important in others, but I agree, that's super interesting development.
Yeah, I mean, it is still very controversial because some people claim they see this everywhere in their numerical box, but today we hear from James Beattie's talk, the volume filling factor is very low. So I think that comes to that part of whether we can test it with the similar conditions and resolution.
So I just wanted to add to the list of observations that I think from my point of view, the one important thing is missing in terms of what I would like to see in 20 years, and these are terrestrial experiments. So Christopher had briefly touched on that, but the regimes we're now being able to start probing like on Earth are getting into astrophysically relevant regimes. So I'm very curious how that is going to develop in in 20 years, like invite people from the like terrestrial experimental community and see how that bridges to like observations and theory and numerics.
Yeah, so I guess in the interest of pissing off some other people. So I wasn't going to say this, but the other thing that was actually interesting in the 2000 turbulence list of topics that you probably didn't read is there was actually a lot of talks on experiments and reproducing the MRI and understanding hydrodynamic turbulence through Quataert flow experiments. And my perspective is that it's been extremely difficult, with a few exceptions, to learn very, very precise things out of those experiments because of the difficulty of having sufficiently precise diagnostics. You can do a laboratory experiment and you get interesting results, and then it turns out it's affected by Ekman pumping and this boundary layer, and it's a really, really hard problem. So I think there's a tremendous amount of potential there, but I think it also requires maybe more care than we first thought / hoped, in that, the laboratory experiments are necessarily of finite size and have their own scale separation issues. And so really getting into the regime and having the diagnostics to know that what you're looking at is probing the phenomena that you care about in astrophysics is actually pretty challenging. So I think it's quite exciting, but very hard.
So along that line, I'll mention a couple of things. So one thing that probably most of the people in this room have not heard about, because it's sort of a groundswell of support for this within the space physics community, is to develop and build a solar wind machine, an experiment that they can study things like solar wind turbulence. Now, a lot of the limitations that Eliot mentions, I mean, things like trying to get a proper large dynamic range between sort of stirring and where we can actually diagnose and measure these things is going to be a big challenge. But there's actually a meeting in Lake Arrowhead in April where they're going to be discussing that and really trying to lay down plans and propose to NSF to build one of these things as a big shared resource. A second thing I'll mention is that, there have been experiments that have studied, small aspects of this. Just down the road at UCLA, there's the Large Plasma Device. My group, along with other collaborators, we've done really very fundamental turbulence experiments in the way of looking at the nonlinear interactions between counterpropagating alphane waves, which sort of I like to call the fundamental building blocks of plasma turbulence. So we've done experiments there. We've also done experiments there on auroral particle acceleration, which I know really lives very much in the space physics regime and probably is of less interest to astrophysics, but it's a particle acceleration problem that you can actually tackle in the laboratory. We had a nice paper that came out a couple of years ago at AAS. The other thing that I'll mention, though, that is not strictly an experiment, but spacecraft measurements are a huge resource for understanding, especially these plasma physics, kinetic physics, dissipation mechanisms, because you can measure all aspects of the electromagnetic field fluctuations as well as the perturbations in the particle velocity distributions. And so those represent what I think is very much an untapped resource for understanding the detailed kinetic physics and testing it in an actual plasma, one that isn't limited by length scales and everything else. There are, of course, limitations of you have single point or maybe a few points where you measure it, but there are techniques to overcome that. And so I think there's a lot of lessons to be learned from establishing better connections between the space physics community. The heliopause is not an impenetrable barrier, and I mean that culturally. So, let's talk more. I started out in astrophysics. I was there on that list in the 2000 program that we had here as a graduate student. It was just an unbelievably awe-inspiring experience to be here. I've sort of, since I got into postdoc working with Eliot at Berkeley, I kind of drifted off into space physics because I realized no astronomical data would enable me to test any of the things I was doing at that time, but spacecraft could. And so I've been living in that world for a long time, but I think that, I've sort of worked on trying to develop the tools to move back into the astrophysics world. So I certainly hope to see a lot more of you more frequently at meetings, and I hope that maybe we can convince some of you to come to some of our meetings a little bit more and get a little bit more communication. I think there's a lot that we can learn from each other in that respect.
I found it very interesting when you brought up the question of what really happened since the last turbulence meeting here at KITP. And you also asked the question, what did numerical simulations contribute to this? Did they contribute anything to our new understanding? So there were a few examples that I remember quite vividly. The first one was the so-called catastrophic quenching of the alpha effect. That was a major problem back then. It had some precursors from the time before that, and it had actually a pretty quick solution shortly after that by Blackman and Field, and really understanding that how one can write down the evolution equation for an alpha effect, which was actually not something really new. It was rediscovered. But it was not fully describing the simulations, which was not known at the time. So that large-scale dynamos is one example. It's not finished the story, of course, but it was that was a major phase transition after that, I would say. Now, small-scale dynamos is another such example. What's going on? Small-scale dynamos is another example. Back then, we were thinking of a double humped spectrum where one has a large-scale magnetic velocity field and a small-scale velocity field of similar height. This picture is completely wrong. We now know this, and there has been a lot of development in small-scale dynamo theory. Sheko Sheehan was one of them, and lots of other people. Another example is decaying turbulence. When people talked about decaying turbulence, they missed completely the subinertial range. it was not included in the simulations. And so the peak of the spectrum in all the simulations was already at the smallest wave number in the domain, so this peak couldn't travel any further left. So these were major basic misunderstandings, and I think they were removed in just the next few years. And then the final example, which we have not really talked about at all, is early universe turbulence. We didn't really know much about this at the time, but after the late 90s, there has been a lot of different papers on this, and now we can also probe, we think we can probe in future the magnetic field spectrum in the early universe through gravitational waves and its polarization and its helicity. So I think there have been a lot of developments since exactly the time when I was at that program in 2000, which was exciting.
Okay, James, do you mind holding off 1 second? I think there's maybe a related comment.
I just want to briefly comment that I don't think that the problem of alpha suppression has been solved in terms of a physically reasonable consensus within the community, and I don't think in particular that the solution offered of preferentially ejecting small-scale helicity from systems with dynamos is the right one.
Yes, that's why this is a bullet unto itself. All right, James, go ahead.
2 points. I think we as turbulence theorists, or people who measure turbulence in our numerical simulations, should look for a gold standard for measuring a cascade. And I think transfer functions are that gold standard. So I think everyone should be trying their best to compute transfer functions if you're doing numerical simulations of turbulence to actually show there's a cascade. You know, fitting something to a power law, that's not enough for me. And the second thing, I think small-scale dynamo theory is an amazing theory. You develop not only all these growth phases of the magnetic field, but you develop a lot of structure in the magnetic field. And I don't know if there's been enough work in working out what the observational signatures of that structure really are. And, you know, presumably this structure is everywhere if we live in a galaxy that's full of small-scale dynamo. And it would be awesome to see more steps within the dynamo, small-scale dynamo community to bridge the gap between observations and the structures that we find in our simulations.
Yeah, there is direct evidence for, you know, very small-scale structure in the interstellar medium, AU scales from scintillation observations. What is the TSAS scale? It's similar. So I think there are observations.
But small scale is just smaller scale than the outer scale of the turbulence. It's not that small scale,
no,
right?
AU.
Yeah, but I'm just saying when I say small scale, I mean scales less than the outer scale of the turbulence. That's small scale, right? Yeah, okay. In the context of small scale dynamo.
Yeah. So I think there are, you know, especially in the Milky Way and using the many sight lines through CGM, there are ways of getting at this observation. We've seen examples of that. All right, anything else?
Just I would like to attract attention of you that the greatest progress of turbulence in hydrodynamics is Kolmogorov incompressible turbulence from the very beginning. And we should not underestimate the importance of incompressible MHD in understanding of turbulence in magnetohydrodynamics. It's a tendency whenever we find some new effect to attribute it to compressibility. But we had this with this decay of turbulence. It's not related to the compressible modes or coupling with the compressible modes. And we have new examples related to that. And therefore, we should not somehow think that in spite of the fact that turbulence in astrophysics has many facets and complicated, that we cannot find effects of incompressible turbulence at the core of these effects.
All right, I was going to wrap up, but yes, go ahead.
Just one small point, because I don't want everyone leaving this conference and thinking small-scale turbulent dynamo fails to produce coherent magnetic field that we can see in observations. I think Ethan mentioned on Tuesday a very nice example is high redshift galaxies. There is rotation measure available. So it's not highly tangled small-scale magnetic field, then we wouldn't be able to see any rotation measure. And also in our own galaxy, the rotation measure, I mentioned this already, also suggests on the order of 100 parsec coherent turbulent magnetic field, and is likely to come from the small-scale dynamo. That's all. Thank you.
All right, thanks everybody for a great meeting, and I look forward to interacting more with those of you who are going to continue to be here. So.
Safe travels, everyone. Thanks for coming. It was great to have you.
Sasha, for helping us and organizing so much and solving all the troubles along the way. There has been so many changes to the program, right? And in the last minute, he was juggling around and getting new speakers online and everything.
But it's not just me. It's Xiao and Greg and Yuan, who was not even supposed to be involved in the organization of the conference. You helped us out so many times. So thank you so much.